Okay, let's start with lecture 4. I think the last 3 lectures, especially lecture 2 and 3, give us almost everything we need to know about rigid body motions and velocities. And so one more important concept is called exponential coordinate, and that's also the foundation for rigid body kinematics. This kind of coordinate, I think we already have all the background to truly understand what this exponential coordinate really means. Okay, it's really taking a operator view of a rigid body transformation matrix. Okay, this lecture we have 3 parts, and the exponential coordinate, and for SO3 and SE3, and in between I will just talk a little bit about Euler angles and Euler-like parameterization for rotation matrices. So these are the set. If you still remember, this is the set for rotation matrices, right? Rotation matrix. And this is set for homogeneous transformation, homogeneous transformation matrix. And the question is that how do we have a better way to parameterize or define the coordinate for those 2 kind of very special sets? To really get us started, let's just remind you there's many different ways to define coordinate. Okay, the things that you guys are very, very familiar with is this complex plane. Now suppose I have a complex plane. This is my real axis, this is my imaginary axis. If I have a point on the plane, okay, I say this is a point P, how should we define the coordinate? The Cartesian coordinate that's mostly commonly used is basically defining according to this projection onto these orthogonal basis vectors, and this is our P of let's call it X. Let's say X of P. This is my let's say Y of P, right? So P can be represented as a coordinate, which is XP and YP. That's one way to represent arbitrary point on this complex plane. And also we can define it equivalently to define this as polar coordinate, right? Using the length or the norm of P vector and also the angle phi. So P can also be written like say polar coordinate, and this is in polar, which is rho of P and the phi of P. At least 2 ways to define, they're all equivalent way to define the same point. This represent the same point, but the different ways to define the coordinates, right? This looks familiar, and but let's jump a little bit more. Suppose I have now let me ask you guys questions, right? Suppose I have a set M. Okay, the first question, M is defined as the following, right? M has 2 coordinates. The first coordinate t, second one is related to the first coordinate, is a sine 2 pi 2n pi t. Fuzhen, is I'm a set, is I'm a set, and what's the, let's say, it's a subset of what? It's a pair of numbers, right? It's actually a subset of R2. You agree?
Yes.
Okay. I hope everyone can see this. This is really a subset of R2. And if we draw this graphically, let's draw it. It's a very special form. Okay, this is maybe 1. This is 0. Okay, let's draw this. Maybe this is 1. This is -1. So when t can range, this x coordinate can range from 0 to 1. Okay, and the y is a function of t, the sine function of t, and depending on what n is. Let's say n equal to 1, then this is sine 2 pi t, which is it's just 1 2 pi. Let's say this is a half. So that's Frozen, correct me if I'm wrong. That should be the sine 2 pi of t, right? Frozen, this is right.
It should be right.
Okay. Now let's what happens if, let's say, if n equal to 2, then integrate this further. So that will be within half, we'll have 1 cycle. Let's say that. Hold on. No, that's 2 pi. That when equal to 2, that's a 4 pi, right? The 4 pi, yes. So it will be like that. Well, I don't think I draw it correctly. If it is a 2 sine n equal to 2 will be 4 pi t, right? So from here will be 1 cycle. That will be this, and here's another cycle. This. All right. Okay. So for this set M covers everything in this square. Graphically not, right? It's not.
Yes.
It's not. It's not that not cover everything
not.
within this. Yeah, within this this square, not rectangle. Okay. Now let me ask Hongbo maybe this time. I say a point. Let's say a point P here. Okay, this is my point P. How do you define its coordinate?
It should be t sine 4 pi t.
Well, you jump ahead of me. Okay, that's fine. P is embedded. I mean, the set is embedded in R2, right? We can use, well, typically we will define this way, right? This will be my XP. Again, just similar to the complex plane, right? This will be my YP, right? So I can represent this XP, let's call it XP and YP, right? That uniquely specify the point P, right? What do you think this is good representation, and what would be the drawback? Hongbo?
Oh.
You think it's good or bad?
Not very good, I think.
Now they're very good. Okay, so it's nothing. Well, it's right. It's correct, right? It depends on how we define good and bad. So the thing that makes it less perfect is that it ignores complete the structure of the set. Okay, so it's in the sense that it didn't take advantage of the structure of the set, because P can only move, let's say, along locally neighborhood of P does not contain all the points near P. It actually only contain points that on that sine curve near P, right? So this is coordinate V. This is not that perfect. To take advantage of structure of the set M. M has a very, very special structure that I artificially make up this M, right? We can define coordinate of P as chord of P as in this case, this is 2, and let's call it XP. Here is XP. Maybe I can just call it XP. Yeah, the notation is a little bit weird. Okay, that's fine. So what does this mean? So it lies on sine 2 and pi p, this curve with n equal to 2 and t equal to xp, right? You first pick which frequency I'm writing, okay? and how far I move along that frequency that uniquely specify a point. If we know the structure implicitly, we can define this way. For the homework, that makes sense?
Yeah, that makes sense.
Okay, so for example, I can also call this guy. I can give another example. Let's say this one, this one. This is another p. Let's say p of 2. They may also have this coordinate. This is a xp2. Okay, so this case p2's coordinate, I can call this 1 and xp2. Okay, so I pick a frequency where n equal to 1, and I ride through this curve. I travel along that curve for xp2 time, and that uniquely specifies my location. Okay, and you also can go back to the Cartesian coordinate as well. All right, so this is graphically, this is small as a whole, but you're clear that we can define any way as long it's like an internal index. As long if we know how to find this point based on the structure of the set, we're good to go, right? And the exponential coordinate is just exactly similar to this case. The set SO3 or SE3 has a very special structure. Okay, if you just ignore all the structure, you will define a pure matrix. But that matrix has a lot of constraints, right? If you want to utilize constraint, exponential coordinate would be best. Okay, it's the same way or similar to this example. I hope you can keep this figure in mind. Then let's move to the more general discussion. Okay, exponential coordinate is based on the following proposition or fact that I somehow didn't prove rigorously before, but I argued through them several times already. Okay, so first of all, if you gave me any unit vector, let's say in unit vector, this is unit vector, norm equal to 1. Just for simplicity, let's only consider unit vector. And any theta, the matrix exponential of this form is always a rotation matrix. That's our operator view of rotation matrix. That's exactly lecture 3. I hope that's fine. So whenever you see this symbol, this is a R3 by 3 matrix, but its meaning is you rotate the point or frame or object around omega hat axis for theta degree. That's an action. That's a verb. Okay, and that's give you a rotation matrix. That rotation matrix can be used as an operator. Okay, this guy always in SO3. I think I argue a little bit about that. You can prove it by the definition of SO3 and also by the definition or properties of matrix exponential. Okay, the other one is the inverse part. For any rotation matrix R3 in R3 SO3, I can always find a axis with the unit axis vector omega hat and the theta such that R can be written as this matrix exponential formula. Okay, so let me be more precise using all the previous notations. This guy, the skew symmetric matrix times theta is in little SO3, right? And that's always correspond to our, if you like, P dot equal to AP. That's our matrix differential equation represent the rotation operator. This A is just this, right? Sorry, this A should be skew symmetric matrix of this, right? And this guy is in little SO3. And if you apply the exponential map, matrix exponential map, that means solve linear differential equation. Okay, you will have a R which is the valid rotation matrices, and vice versa. If you throw me any kind of rotation matrix, no matter how you got the rotation matrix, as long as it satisfies rotation matrix properties, you can actually find, okay, the inverse map of that. we will call the matrix log. Okay, log of it will give you the rotation axis and also how much, or what's the degree that you rotated about that rotation axis. So the vector here is called the exponential coordinate for R. I want you to make an analogy with this respect to this figure. Okay, R. Let's make a few more comments. R is a n by n matrix that has 3 by 3 matrix, has 9 numbers, right? So it's a subset of R 6 by 3 by 3. It's a subset of 3 by 3 matrices. Okay, but it has some properties. It's cannot take arbitrary values in R3 3 by 3, and to take advantage of the structure, this guy can always be obtained by selecting a particular axis and tells you how far you move along that axis. Use that as the exponential coordinate for R. Okay, as a coordinate. Because of the special way of this mapping, use matrix exponential, so we call it exponential coordinate. Let's go back to this example. The coordinate that I define here, I can call it sinusoidal coordinate for the set M. Okay, so to represent M, I pick a frequency of the sinusoid, and then tells you how far you move along that frequency for how long. And these two things uniquely specifies my current position. So that's another way to define it. I can call it sinusoidal coordinate. Okay, so similarly, we call this guy exponential coordinate for things in R. Okay, I hope that's clear now. And exponential coordinates are also called canonical coordinates for rotation group SO3. That's very, very important, elegant coordinates. Okay, that's one way to define coordinates in the SO3. Because of that, and we can actually define some kind of formulas that move you back and forth between these two, little SO3 and the capital SO3. Let's take a look at the definition of matrix exponential. I hope everyone still remember. Matrix exponential of this form, this is our R, right? Rotation matrix can be always written like this form. And by definition, this is a summation, like a Taylor expansion summation of this kind of infinite series. And by this definition, we can have an analytical formula. This is analytical formula. If you gave me a unit rotation axis, tell me the rotation direction, and tell me theta, we can find a, of course, you can compute it in MATLAB or Python, right? That's exponential m, exp_m will give you the numerical values of these matrices. But if you want to find analytical formulas, here is the formula. It's a closed form formula. Yeah, it's a closed form formula. And how do we derive this formula? I can derive it. This is pretty important. It's called the Rodriguez formula. I think computer vision people also use that quite a bit. Okay, not only for control or robotics. This is very formula. Let's just say, by definition, we can derive it right away if you know a few facts. So let's say, suppose omega hat is 1. That's unit vector. This formula applies to unit vector omega. If it's a non-unit vector, you would just say, if this guy is not unit vector, you just need to normalize it and put the scaling to the theta part. Okay, you just need to rotate a little bit more. If x hat is a unit vector, then we have the following. Skew symmetric, of course, is this transpose. Take transpose will give you a negative sign. That's the definition for skew symmetric matrices. This has nothing to do with norm being 1, all right? But if I do this cube, it's actually negative omega hat. So that utilizes the skew symmetric, the unit vector property. Okay, and what else? if I do this omega hat fourth, I will have omega hat cube times omega hat skew symmetric is negative omega hat squared. All right, those are the facts. So whenever you have a cube, you have to take a negative sign and you reduce this from 3 to 1, right? Was 4, then I can reduce by 2, take a negative sign as well. So by using this fact, you can easily verify the fact by skew symmetric matrix properties and the fact norm of this omega hat is 1. Then we can say exponential this with theta equals to plug in this one, right? I plus theta times skew symmetric plus half factorial is also, so 2 factorial, and this guy is cube plus theta cube divided by 3 factorial. What I have here would be, let's write it down, cube, but this guy equal to this, right? So I can change that to negative omega hat this. Okay. I will skip some steps, tells you that this 4 factorial, because this guy equal to negative skew symmetric matrix squared, I can write like this, and the plus dot dot dot. Okay. Eventually, if I group terms, this is identity plus theta. Let's group the odd terms. Theta is negative, right? So negative theta cube divided by 3 factorial. Also times the same thing, right? Omega hat skew symmetric. If you can remember, if you took a 5th power, then that's become the same thing, which is also related to that. Okay. Plus dot dot dot. So all the higher power, the odd number will reduce to this. The even power will reduce to this guy. Okay. So plus theta squared 2 factorial minus theta 4 factorial plus theta 6 factorial dot 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 omega hat squared. Okay, so if you can recognize this guy is a Taylor expansion for sine theta. Okay, this guy is 1 minus cosine theta. Okay, overall, I will have this whole thing becomes an expression of the Rodriguez formula. Okay, have an expression, analytical expression. Of course, you can numerically compute through software anytime, but this is analytical. Okay, let's look at example. Now, suppose I have a rotation matrix, this x theta, that means corresponds to the exponential map. This is exponential coordinate is x hat theta. What does this mean? I mean, hold on. I mean this guy, by definition, is the rotation operator. Let's call it rot about x hat axis for theta degree. Okay, so by our previous result, this is matrix exponential of x hat times theta. Any questions? All right. We have analytical formula now, right? We don't need to plug in numerical value. So in analytical formula, I have this one from the Rodriguez formula. I have identity plus sine theta times skew symmetric matrix of omega hat. In this case, omega hat is x hat, right? Suppose I'm using the canonical coordinate system. This is 1, 0, 0. Okay, rotate about current frame x hat. So that's 1, 0, 0. 1, 0, 0. This skew symmetric will be x hat would be what 0, 0, 0, 0, 0, negative 1, 0, 1, 0. Okay, that's skew symmetric. That. So overall, I will have this is 0, 0, 0, 0, 0, negative 1, 0, 1, 0, plus 1 minus cosine theta. You can multiply this. You can take a square of this, which will be, I think, is 0, 0, 0, 0, negative 1, 0, 0, 0, negative 1, I think. Let's see. Overall, you will have, eventually you will have 1, 0, 0, and this is cosine theta, negative sine theta, and cosine theta. That's I think a lot of people saw those kind of equation before, but we can obtain it through this operator view and also use the Rodriguez formula. Okay. This means rotate about x-axis by theta degree. Okay, but of course, this can also represent the orientation of the R, of certain R, relative to the initial orientation. So if you rotate R from the initial frame to a final frame, and that's rotate operator, and the final frame orientation is also given by this, right? And the rotation matrix corresponds to this. This is the exponential coordinate, sorry, the exponential coordinate. What does this mean? This is not unit vector, right? So this guy is, so omega hat would be 101 times square root of 2. Okay, and in this case, theta is square root of 2. So this coordinate means this coordinate, let's say exponential coordinate 101, actually represents a matrix e to the omega hat theta given by this. I wouldn't want to compute this. Of course, you can use the Rodriguez formula to obtain an analytical formula for this R. It just gives you exactly as you rotate, as theta increase, how the rotation matrix behave. It's the analytical form of the 9 numbers in the matrix. And also you can compute numerically anytime for any particular theta. Any questions so far? The other one is also, this is a forward map, okay, from little SO3 to capital SO3, how to obtain from the rotation axis or exponential coordinate to the corresponding rotation matrix. You just need to compute the matrix exponential. And also, if I gave you a rotation matrix, you should also tell me what is the exponential coordinate. Okay, that's you need to take a log. Okay, I don't want to derive it. You can easily verify these formulas. There's 2 cases. If R is 3 cases. If R is identity, then nothing rotates. You can think about any rotation axis, it just rotates 0 degree. So it remains as the before, as the original frame. And the special case, we can, let's see, equal to 1 of the following. So omega hat can be defined like this. And for otherwise, theta is this, and omega hat is given by this. So this can be easily programmed. Once you give me a matrix, I can take a matrix log. That's somehow very easy to program. You can use model robotics toolbox, or you can program by yourself by using these formulas. Okay. Now we have learned the exponential coordinate of SO3. Hopefully that's clear. So you can use a rotation axis and how far you rotate along that axis to represent any rotation matrices in SO3. And we know how to move back and forth between SO3 and the little SO3. Okay, hope that's clear. But in robotic, in real applications, most people often use Euler angles. Okay, I want to briefly mention that. I think that's clear for many of you. So a common method to specify rotation matrix is really through three independent quantities called Euler angles. And how do we obtain the Euler angles? We view, this is our final orientation, let's say, orientation. This is 1, right? This is our initial orientation. I think I use other symbol. This is called alpha. This is my beta. This side is our gamma. Okay. So suppose this is what I want to represent, the orientation of Z1 relative to X0, not Z1. So frame 1, this is the frame 1 relative to originally, this is the frame 0. And Euler angle representation also through few actions. Rotate this, initially these two are the same, right? And we assume the difference, the orientation become different because of three independent actions. The first one, you rotate about Z0 by angle alpha, then rotate about the next YA axis by beta, and then about ZB. Again, it's often sometimes called ZYZ angles. Okay, so in our notation, the orientation of 1 relative to 0 is parameterized by this. And this is nothing but the parameters or degrees for each individual rotation. Okay, so this is what? This is rotation about Z axis for alpha degree. Okay, this guy is rotation about Z axis for gamma degree. This is Y axis, right? So so for example, each of these, I can compute this, by the way. So RZ gamma is what? Is basically rod. So let's say this is matrix exponential. So exponential of Z hat times gamma degree. All right, you multiply them together, you got this thing, and these parameters give you the Euler angles. There's many different ways you can rotate first about Z and then Y and then X, or Y, Z, X. These are, you can make several different choices. I don't think that's particularly important. Okay. Now let's think. I have 10 minutes. I can finish this. You can see that our discussion often somehow have more details in the rotation part, and then translation is become similar. Okay, because we understand SO3, so we can now start to generalize it to the exponential map for from little SE3 to capital SE3. Okay, this is also based on the same fact that we discussed several times before. So any twist or screw axis, okay, any twist and give any theta number, we have this one is in a this is a valid homogeneous transformation matrix, as I mentioned before, homogeneous transformation matrix. Okay, you can derive it, or you can prove it by construction. You can always construct find the solution and find the particular form of the this matrix exponential. You find out it has a valid form, satisfy all the properties needed for SE3. Okay, these are the formulas. I don't want to derive them. All you need to know is that if I gave you a twist in R6, right? Twist in R6, you have omega and V. Okay, and the matrix representation of twist is 4 by 4. Okay, that came from our linear differential equation view of the rigid body operation, right? So this is take this part, and this is v 0 and 1, right? This is 3 by 3. This is the 3 by 1. This part, okay? That's a matrix representation of a twist 4 by 4, and we know the matrix exponential will give us theta, will give us a 4 by 4 matrix, and it turns out this matrix always a valid homogeneous transformation matrix. Okay, that's what exactly this means, and we find a solution, analytical form for this mapping. This is also called forward exponential map of from little SE3 from little SE3, that's in little SE3, okay, to a capital SE3, which is the set of all homogeneous transformation matrices. Okay, now the other direction, if you gave me a homogeneous transformation matrix, I can always find a twist or a screw axis. They are interchangeably. This is almost like a normalized twist. And the scalar theta such that T can be viewed as the operator which rotates about the screw axis S for theta degree. Okay, so these are given. I can always find the S and the theta such that this expression holds. This is also called logarithm of SE3, capital SE3. If you give a homogeneous matrix, I can always find screw axis. Graphically, I want to repeat that again. Suppose initially I'm here, this rectangle is here, and you give me orientation, let's say now it's here. Arbitrary orientation, okay? Then I can find a screw axis somewhere here, so that the operation is just move this guy along the same constant screw axis for theta degree. Okay, this mapping is exponential of S for theta. If you give me another one, if you give me here, maybe this one, okay, I can also find another screw axis, and let's see. So maybe this will be the way. Hold on. Well, my drawing is not accurate, but giving me arbitrary orientation, give arbitrary homogeneous matrix. Okay, then we can find the screw axis to realize it from the beginning to the end. That's the meaning. Okay, the operator view of T gives the exponential coordinate of the SE3. Okay, so because of this one-to-one mapping, we can sum up a screw axis consists of this is equivalent to say S hat QH, right? This has a twist or spatial velocity representation, and also the more natural representation. Screw axis can be expressed as a normalized twist. Its matrix exponential, of course, it's the same thing. It's just a special twist that rotates, follow the screw motion. A point started at P0. I'm just reviewing a little bit about the differential equation view. At time 0, travel along screw axis at the unit speed for time t will end up this P of t. Okay, in this homogeneous coordinate, that's the solution of the ODE, right? That's the solution of the ODE, which is as P tilde. That's the ODE. That's the ODE tells you rotate that point about the screw axis for time t, right? The solution is given by matrix exponential. And so given as using theorem 1, we can compute this. That become operator. Okay, operates or applied to, this is dot, okay, applied to P at the beginning to the P after the operator. Okay, this is a matrix exponential. Sorry, this is in homogeneous transformation matrix. And given any homogeneous transformation matrix, we can use theorem 2 to take the log and to find square axis and theta such that the relation holds. So we call this one as theta, the exponential coordinate of homogeneous transformation matrix T. If you want some graphical figure, just think about this one. All right, given any T, this is my T, okay, orientation relative to the initial, we can always write this T as E as theta. We can think about this T as applying this operator to the initial configuration and move to the back by following one square axis S for time T equal to theta. Okay, I think after we know the operator view of homogeneous transformation matrix and rotation matrix, matrix potential becomes easier, right? I'm not sure how, do we have any questions? We're almost done with this, the foundation. Next time we'll start talking about the Ricci-Body kinematics, and it's built upon this matrix exponential concept.